Everyone, so let's continue what we were doing with the Hodge conjecture. So quantifiers allow us to manipulate objects in any way that we can based on the definition of the quantifier. So quantifiers allow us to manipulate objects So first of all, there is a universal quantifier. This is for all x. For instance, for all x in the real numbers, x squared is bigger or equal to 0. That's a statement which is true. Existential quantifier there exists an x inside of the real numbers, for instance, such that x squared is equal to 4, that being the square root of 2, square root of 4, which is 2, and minus 2. So there are methods of proof. There is a direct method. So there is direct proof. And what direct proof is, for instance, you have the following theorem. Theorem 1.1. The sum of two even numbers is even. The sum of two even number is even. Proof. Suppose n and m are even. So that means that you have n is equal to 2 multiplied by k, and m is 2 multiplied by p. So that means that n plus m is 2 multiplied by k plus 2 multiplied by p. You can take 2 as a common factor. So you have k plus p, where k plus p is equal to s, which belongs to the integers. So that means that this is 2 times s, where s belongs to the integer. So that means it's an even number. There is also proof by contradiction. So we have the following theorem 1.2. So let's look at proof by contradiction. So we have square root of 2 is irrational. So square root of 2 is suppose it's rational, p over q, then square both sides. And move things around, you get p squared times 2, or q squared times 2 is equal to p squared. You can show that means that that means that p squared is even, which means that p is even. P squared is even. You can show it by the prime factorization theorem. P squared is even, or I mean, like, if you want, p squared has a certain prime factorization. If it has 2 in the prime factors, that mean, since we're multiplying, p has a prime factors as well, where they both must add up to one of the factors that p squared has must come from the prime factors of p. Otherwise, there will be gap in the lattice. So that means there will be gaps in integer where something just comes out of nothing. So that means that p has 2 in the prime factorization. So that means that p is even. So which implies that p is even. So that means that you can cancel. That means you can cancel a 2 in both sides, and you get that 2q is you get that p is even. So that means that q must be even, and then you get that we have p and q are both even, where even though you can start with 2 numbers, p and q, that are simplified. So you cannot factorize them more than that. Otherwise, you can keep doing the argument and factorize them until you get to the most factored form. So if p is even, then that means that p is 2 multiplied by k, which means that 4 multiplied by k squared is equal to 2 times q squared, which means that q squared is 2 times k squared. So then that means that q squared is even, which implies that q is even, and we get a contradiction. Alright, there is also mathematical induction, but I will do that in the next video. So I will see you guys soon. Bye.